So yeah, today I want to tell you about a topic that's very recent. So it's a paper we just posted that I hope will fit the theme of this conference pretty well. And so, yeah, it has to do with hydrodynamics and also two topics that are close to my heart. And so in a nutshell, my goal will be to provide or construct some effective field theory, or classical effective field theory for monitored classical systems. I'll explain what I mean. And so at the same time, I'll explain precisely what I mean by monitoring classical systems. And at the same time, I will also, you can think of it as a theory where you have something like hydrodynamics, and you add measurements to it. And again, I'll explain precisely what that means. And somehow you get completely new fixed points and behavior. Okay. So this is work done in collaboration with Ewan and Sarang, who was here earlier this week. And again, it's posted, but also sort of work in progress. We got scooped on this, so we rushed a little bit. So we're still working out a few aspects of the story, so if you have comments or anything, that would be great. Okay, so my talk will be roughly split in two parts. Since we have a broad audience, I'm going to first tell you a bit about where I'm coming from on this and tell you about monitored quantum systems and some recent questions related to measurement-induced phase transitions. So I apologize, I know some people in the audience are very familiar with this, but some not so. And then I'll switch to hydrodynamics. I will explicitly have conserved quantities, and the second half of the talk will be entirely classical in some way. Okay. All right, so let me start with, again, no hydrodynamics, and purely just telling you a little bit about monitored quantum systems and kind of questions that people are asking, okay, and why I want to mix this with hydrodynamics. Okay, so the kind of broad motivation is this era of noisy intermediate scale quantum devices and the fact that, if you want to think of many-body quantum dynamics in kind of a general way, in those systems, you kind of have to think in terms of what people like to call interactive or adaptive many-body quantum dynamics, where you not only have to think of the environment, that's the N in NISC, and so you have an open quantum system, but you also really want to think of the observer, okay? And since you have a quantum system, measurements are part of the evolution, right? They're real effects, and they can occur on the same time scales as your dynamics, okay? That's really would be part of thinking of something like active quantum error correction as some type of very general many-body quantum dynamics, where you have noise, you monitor the system, and you perform feedback based on the measurement outcomes and so on. Okay? So that's kind of a very general type of open quantum system. So really, this will be the main idea behind this talk of thinking of measurements as being part of quantum dynamics. Okay. So I'm sure many people are familiar with at least basic effects of measurements in quantum mechanics, right? We all know at least about the Zeno effect, which is something we learned early. You can know that measurements can not only destroy quantum entanglement, but it can also induce long-range entanglement, right? And a famous example is that of quantum teleportation. If you have two Bell pairs, like you have A and B, qubit A and B in a Bell pair, C and D in a Bell pair, they don't talk to each other. If you measure B and C in a Bell basis, you can induce some entanglement between A and D, okay? So it's something to keep in mind. Measurements can both destroy and create entanglement, okay? Okay, so the general idea of this talk will be, again, to do this in a many-body context, both quantum and classical, but let me start with quantum. Okay, so assume we're all familiar with measurements in the context of a single qubit. Okay, so you can do a projective measurement. You just project onto a classical bit, you get your 0 and 1, and you project your wave function as a result. So in this talk, I'll be thinking about this, again, in a many-body quantum system, We'll do this in any dimension, but let me draw things in 1D for simplicity. So, okay, so this, never mind, I'll just point the old-fashioned way. So I'm going to imagine I have a system with like, a bunch of, say, qubits that are prepared in some states, and then they undergo some evolution, and this could be pretty much anything you want. It could be your favorite chaotic Hamiltonian, or it could be a quantum circuit. And on top of this unitary evolution, which is this blue box, we'll sprinkle in some measurements, okay? And those measurements are kind of, they call mid-circuit measurements. They occur at some specific space-time locations, okay? So imagine you have the ability to individually measure like this qubits and not touch the rest of the system, right? So you don't project your whole wave function, you just measure the state of the qubits. And when you do this, you collect measurement outcomes. I'm going to call them M. So M will be bit strings of zeros and ones. That's like the data you collect as an experimentalist, and we're going to call Eve the observer collecting this data from that experiment. Okay. So it's important to note, like in this picture, like the state of the system remains pure, right? This is not a mixed state evolution. The wave function is labeled by the I'm going to label the wave function by the measurement outcomes M. Okay. This is called the quantum trajectory, and this is still a pure state labeled by those measurement outcomes. And the time evolution operator is obviously not unitary anymore because you have the measurements. Okay. So if you want an equation for what the evolution operator is, you can think again it's this blue box. It's a bunch of unitary evolution with some projectors onto the measurement outcomes that you get. So in the way I wrote it, this wave function is not normalized. You should normalize it before computing anything physical. And in fact, its norm squared is the Born probability to observe that particular series of measurement outcomes in that experiment, right? And if you sum over M that quantity, you just get 1. Okay? All right. Very good. So one important point is, in this talk, it's going to be really crucial that we do something with the measurement outcomes, and you'll see this will be the same for classical systems. So meaning if we throw away the measurement outcomes, we don't do anything with them, then we're effectively back to a case where you have an environment, right? So we imagine if you have an open quantum system, you can think that the environment is effectively monitoring your quantum system. But the crucial difference with what we're going to talk about, if physically you don't have access to whatever the environment measured, so you don't have access to that information, which means that anything you can measure physically is going to be given in terms of that density matrix. So now your system is in a mixed state, a classical superposition of measurement outcomes. Okay. So whenever you write like a Limblad equation or a quantum channel for open quantum systems, you're dealing with that object. And one realization of recent years is that there's non-trivial physics when monitored systems that does not occur in this open quantum system context. So you really need to do something with the measurement outcomes to see that physics. Okay. So you have some non-trivial physics in those quantum trajectories that is invisible in that quantum channel or open quantum system thing. So what type of transitions are we talking about? Well, so this was really, so this was triggered by those 2 beautiful papers by Skinner, Ruman, and Nahum, and Lee, Chen, and Fisher, quite some years ago now. And the most famous example of these are called measurement-induced phase transitions, and that's really roughly what this talk is going to be about. But I'll be thinking of those transitions in a language that's maybe a bit different. So they're sometimes phrased in terms of entanglement. I'm going to be thinking really in terms of information that you collect from the measurement outcomes. And this is this perspective that will translate to classical systems as well, and to hydrodynamics. Okay, so what type of questions are we asking? Well, so in order to see those transitions, or at least one way to see them is to think of some kind of process like this, where you have Alice trying to transmit some quantum information to Bob. So you can imagine that Alice has a qubit worth of quantum information, and she's encoding it in a larger Hilbert space. And then that system is undergoing some monitored evolution, So you have an eavesdropper, Eve, trying to kind of learn that information. And at the end of the day, you have Bob, who's trying to decode that information despite the interference of Eve, or Eve trying to learn something about what Alice was trying to send. Okay. So again, if that sounds abstract quantum information, mumbo jumbo to you, it's okay. We'll make this maybe a lot easier with just classical hydro things, right? So that's somehow basically the goal of this talk. Okay. Okay, but it turns out like asking such questions that leads to non-trivial phase transitions as a function of the rate of measurement, or how scrambling your system is, basically, okay? So there's a competition between your dynamics that's like hiding information from the local measurements and the rate of the measurements. Okay, and so in this talk, I should say I'm going to take the perspective of the eavesdropper. So I'm going to imagine an Eve here. I'm trying to learn information from the measurements. Okay. You can also ask what happens to Bob, but that's not what I'm going to do here. Okay, so this is just a remark that's also related to questions addressing complexity, but okay, that's not what I'm going to talk about today. Okay. All right, so there's still no hydro here, still no conserved quantity, but let me illustrate just in one slide how you can think of those transitions in a kind of concrete way. So I'm imagining this protocol where Alice has two quantum states, psi0 and psi1. And those states are orthogonal and, say, random. Okay, so you can imagine you say you had a system with qubits in 1D, you had, again, a Néel state or a ferromagnet. Okay, those two states are very easy to distinguish locally, so say you scramble them by acting on them with a big random unitary. So they remain orthogonal, but they are like very easy, not easy to distinguish locally. And then those states undergo some monitor dynamics, and I'm being vague here because it could be pretty much anything you want, as long as it's chaotic and not fine-tuned. And you have some measurements, and the measurement rate is called gamma. Okay? And so then Eve is collecting some zeros and ones. Yeah. So you do those measurements locally in some kind of random way, random location with some rate gamma, and for a time of order L, where L is the number of qubit that you have. Okay. And then the rule of the game is that from those zeros and ones, Eve should try to distinguish, to guess what the initial state was. Okay. Either psi0 or psi1. Is the setup clear to everyone? Yeah. Okay, so you just get those zeros and ones, and you don't know anything about the dynamics. So Eve knows precisely what the dynamics is, what your Hamiltonian is, what the gates are, where the measurements are, everything. So the only thing that Eve doesn't know is which state you started with. Okay, and from those zeros and ones, that's the information you're trying to gather from the measurement outcomes. Okay. Okay, so what I'm plotting here is the probability of success of Eve to do this as a function of the measurement rate for a specific model. This is exact numerics. And what I'm plotting is actually the provably best that Eve can do. Okay, so that's, if you want, that's the optimal accuracy or probability of success of Eve here. Okay, so what you're supposed to see here is that a small measurement rate, this probability of success is near 1/2. Which basically means that, you know, Eve might as well just flip a coin. And she has no idea which state it was, and she could just guess at random. Okay. But as you measure more and more, you see that you start doing better than 1/2. Okay. And of course, what you're supposed to notice here is that there's a crossing. This is finite size numerics. There's a crossing where, you know, if you lovingly extrapolate this to the thermodynamic limit, that's where the dashed line is. There's a phase transition as a function of this measurement rate. So notice that even if you measure a lot, it doesn't go to 1. So it's not like it actually goes to 3/4, and it's something that's very easy to show. So even if you measure a lot, it's not like you can, with 100% certainty, tell which state it was, but you can do better than flipping a coin. Okay? And so you have two phases. There's a phase where Eve doesn't learn anything. At least in the thermodynamic limit, you see like this will actually go to 1/2. So there's a phase in which the measurement outcomes essentially contain zero information, might as well be random rubbish, okay? And there's another phase where you actually, Eve can actually learn something from the measurement, okay? And so that's the type of transitions I'm gonna be talking about. Yes? Okay, yeah.
Can I ask real quick? So, I don't work in this field, so
yeah, that's good.
But,
yeah.
But I've heard like this thing called shadow tomography, where that's another way to guess the state by applying these random geometries. So what's the difference from that that you're trying to achieve?
Yeah, so this is a very non-optimal way of doing it. So shadow tomography, you do it at the end, and you only define the game so that I only have very partial information. I'm only measuring like locally 1 qubit, and I have a finite density of those measurements. Okay, so I'm purposely making it hard for myself to recover some information. Whereas when you do shadow tomography, you actually want to reveal as much information as possible. So I'm purposely thinking that I only have very limited data here.
But some of these transitions that you're talking about, will it also show up in the shadow tomography?
There's a way to rephrase them in terms of shadow tomography. So this learnability, so in this language, I call this a learnability phase transition. So there's a phase where you can learn, and there's a phase where you don't learn. And you can rephrase this. There's a paper by Matteo Ippoliti and Vedika Kemani that rephrases it in the language of shadows. Yes?
So are you also, you're measuring and also doing some unitary evolution, no?
Correct.
So then the point where the transition occurs would depend on how strongly interacting the...
That's correct. So there's, if you want like this threshold here, yeah, it will depend on how scrambling your dynamics is.
But there will always be a phase transition.
Yes, as long as your system is interacting, it's not free fermions or something like this, and okay, at least it's not specific enough, right? So I'm assuming it's generic here.
Is there a simple way to understand the scaling, like you need only linear in time, linear in system size time, or?
I'll come to this in the next example that will be more classical. I'll give you some intuition. So actually, you could make this any polynomial of L, and it would still do the same. So this could be L squared and L cubed, and this would
not exponentially in L.
Yeah, if you went to exponential time in L, you would start learning here as well. But yeah.
Very naive question. So why it is saturated at 0.75?
Yeah. Well, so you can imagine even if you take those states and you just measure everywhere, well, then you killed your state. There's nothing left you can do. But that gives you only very partial information to distinguish this. And there's an easy calculation to show that you can get 75% accuracy to distinguish states. Yeah. Any other question about this setup?
So order L is the kind of optimal time, is it? If you do larger, it doesn't improve.
I mean, it doesn't improve in the sense that you will still have a phase transition. The curves will vary a bit for finite systems.
But it still saturates at like 0.75.
Yes.
And you can
Correct. Yeah. Okay. So that's the basic type of setup I'm going to be talking about. And again, I will make this as concrete or as classical as possible in the rest of the talk. Okay. So the motivation is kind of understanding those phase transitions. And so, okay, let me get closer to hydrodynamics now. So one thing we did already a few years ago now was to add a bit more structure and symmetry to this problem. So you can imagine now you have still a quantum system, but you add a U1 conserved quantity. Okay, so you imagine you have a many-body quantum system with a conserved charge. So if you have qubits, again, the 0 is no particle, 1 is a particle, yeah. But otherwise you play the same game. And your initial states now have a different global charge. So imagine you have a state that's at half filling, and another state that's half filling plus 1 particle. Okay, so 1 million electron, 1 million plus 1, yeah. And but otherwise it's the same game. So you have some quantum evolution. I drew a quantum circuit, but again it could be your favorite Newtonian. And you have some measurements, but here you measure charge. Okay, so Eve is measuring locally, do I have a particle or not? Okay. So you measure, you sprinkle some measurements, so here you measured, you found no particle, and here you found a charge. Okay. And you ask exactly, you play exactly the same game. So you ask, can you distinguish those two states? Can you guess whether I started? Okay, so here you look at this picture, and basically you have to guess what the charge of the system is. So charge is conserved. Okay, so for example, you can tell that charge is larger than 2. Yeah, and maybe this particle is the same one as this one and this one, right? And you can kind of follow and try to guess or infer from this data what the total charge of the system is, okay? So essentially, you're trying to learn the global charge of a state of a system from making local measurements in this dynamics. Yes?
Can your local measurements change the conserved quantity?
You measure charge, so it commutes with the charge.
I mean, you measure the local. Okay, it's like a sum of things that.
So it's everything is U1 conserving, like yeah. So of course here, notice that if you measure every single qubit, you know what the charge is, so you're done. So here, if you measure everywhere, you just get 100% rates, and okay. So here, of course, you start to see this is going to have to do with diffusion, right? So we're asking about something a bit more classical here, but it's still a quantum system, and it turns out that there is, so what we realize is there is a phase transition in that setup as well that we call charge sharpening, and that has to do with this learning process, whether you can learn the charge of a system in a chaotic evolution from like the rate of measurements. Okay. So I'll tell you a little bit about this, and again, then I promise we'll switch to entirely hydro type things. So the claim is if you take a many-body quantum system that has a U1 conserved quantity, as a function of the measurement rate, there's actually 2 phase transitions. So if you don't measure it too much, and those, when I say phase transition, I should really clarify, those are not phase transitions in your usual quantum or thermal phase transitions, right? They're purely transitions in terms of this information that you extract from the measurements. Okay, so whether you want to define this as a phase is up to you, but I claim those points here are actual second-order phase transitions for which we're going to try to write down field theories. Okay, and that's what the talk will be about. So, okay, so if you don't measure too much, there's a phase, quote unquote, that we call charge fuzzy, where essentially like this learning process of the charge fails, where Eve cannot really distinguish states with different charges. If you started from a quantum superposition of charges, your measurements are not really efficiently collapsing that wave function. But so there's a threshold that I call P sharp, above which Eve can learn the charge. So if you want the measurement outcomes where uniquely is value of the charges. And here you actually do this with 100% accuracy in the thermodynamic limit. So if you want that partial information that you have is enough to exactly tell you what the charge is. Okay? And really like distinguishing again like charge density 1/2 and 1/2 plus 1/L. Right? We're really talking like not only learning charge density, you're learning it to resolution 1/L. Okay, and there's another phase transition, which is also the phase transition that you get without symmetries, where here you start learning things beyond charge. So you start to be able to distinguish states within a given charge sector. Okay. And so for the rest, so this phase transition is what people call the measurement-induced phase transitions that you might have heard about, and when people talk about it, they usually phrase it in terms of entanglement. And so in this talk, I will largely think about this class of phase transitions here that also occurs in classical systems. And that I claim will have to do with hydrodynamics. Yes?
Do you think there exists a dynamics such that there just isn't a charge sharp phase?
Yeah.
Yeah.
Yeah, so we don't have a good proof that this is always there. I mean, we have models where for sure it exists. It could be that those two coincide. Yeah. Generically enough, I'm sure this is the right phase diagram. It could be that there's specific models for which this phase just disappears. Yeah. Yes.
So about PCs, what kind of observable does it use to distinguish us in states?
Right. So I mentioned, so you can start talking about entanglement of trajectories, which I don't want to do. I don't want to talk about entanglement here. Or you can, well, I don't know if you want to define this as an observable, but this would be it. Like distinguishing states within a charge sector would tell you what that transition is. Okay. All right. So let me emphasize that those phase transitions, like I said, are actual phase transitions. So meaning you can define timescales, for example, for collapsing like a charge superposition, and they differ in the different phases. you can also see those phase transitions in correlation functions, right? So you can define, for example, equal time correlation functions, so charge correlators. Notice that there's slightly weird correlation functions. So the correlation functions define in a given trajectory. So they're defined in what I call psi n, so going back. So those are correlation functions in this state, okay, in a given trajectory. And then you average over those trajectories afterwards. This is actually nonlinear in the density matrix because of the second term. So this is, if you think about it, it's maybe a slightly unusual correlator. But if you define those, this is well defined mathematically at least, right? This is perfectly fine correlation functions. And those have different behavior in the different phases. So for example, it goes 1 over x squared here, and is exponentially decaying there. And I'll tell you why that is in a minute.
This is in 1D, in higher dimensions.
I'll talk about, you'll see what happens in higher D. Okay, so maybe that's going back to Camille's question. So how do I understand the timescales? So here I can tell you why it takes time L. So intuitively, this, there's a lot of this that you can understand from fairly intuitively. So learning charge is not nearly as complicated as distinguishing generic many-body quantum states. Okay, you can get some intuition from even central limit theorem. So if you have, let's say you have very sparse measurements, your measurement rate is very low, then you can imagine your measurements are roughly independent, right? So you just measuring 0, 1 just locally, and those measurements are not really correlated. And okay, so if I give you uncorrelated measurements of zeros and ones and I ask you to evaluate the charge density, you would just average it, right? That's maybe the most naive thing you can do. Like if you find 50, you do 100 measurements and in half of them you find a particle and the other half no particle, you guess you're at half filling. Well, okay, so then this is just governed by the central limit theorem. And if you want to distinguish a charge density that's 1/2 and a charge density that's 1/2 plus 1 over L, you're going to need L squared measurement to resolve that. Okay. And so given that we have a finite density of measurements that corresponds to a time scale of order L. Okay. So here you see you actually, if you went beyond time L, so if you went to L squared or whatever, this phase would disappear. You would just learn the charge always. Okay. So that's the worst you can do, right? If your measurements are independent. In real life, they are very much not independent. They get hold by charge conservation and hydrodynamics and things like this. And so you can do a lot better than this. But that's the worst case scenario.
So the average, the first average is over the trajectory, which is like a time average, right?
So this is equal time, and then you average over measurement outcomes. So this is go to the steady state. So I ran this for a very long time. I compute in the steady state of that system, going to time whatever, L, 10L, whatever, and you compute those correlations, and then you average through the trajectories.
So it will be independent of initial state because of...
It will become independent of initial states, yeah. And that's the type of stuff we'll get from field theory. All right, so that's my last slide on this first half of how do we know all of this, right? Well, so we have a lot of technology to deal with such systems, at least when the dynamics is given by a random quantum circuit. Okay, so we heard about this in particular in John's talk. So it's very similar tools. You can, it turns out you have very powerful mappings between the dynamics of a monitored quantum circuit and some kind of effective magnets. Or stat-mech model. Okay, so I'm not going to talk about this, but from this you can kind of trust me that, for example, in the case of this charge sharpening phase transition with a lot of effort, you can go with, you can start from your monitored quantum dynamics, goes to a stat-mech model, and then write down the field theory of a stat-mech model. I'm not going to explain what this field theory means here right now, but we'll get to this in a much easier way. Okay, so this is something that has replica indices and things like that, right? And so what I'm trying to convey here is that this phase transition we have a good field theory for, which is controlled. But we got it with, after a fairly long and painful calculation. And I guess part of this talk will be to try to convince you that this follows in a way that will be hopefully easier to understand for this audience purely from just a diffusion equation. Okay. All right. Is there any, so that's the first half of the talk. Is there, maybe that would be a good place to stop and ask if there's any more question about just general setup and the type of questions.
To obtain this effective Lagrangian, do you need to first go to the StatMech model? Or how do you
Yeah, so the steps are roughly, so you start again, this is monitored quantum dynamics, and you're asking about those information questions. That seems hard. So it turns out there's star mapping, and like, again, many people have been working on this, where you could turn this into something that looks more like a lattice magnet, like a, roughly speaking, an Ising model, but more complicated. That has some, so the caveat is there's a replica trick somewhere. You need to take some replica limit of that StatMech model. Once you have that StatMech model, you can play usual games. We want the, and it turns out that in the case of the StatMech model, when you have this U1 symmetry, you can write an effective field theory for it. It requires like integrating out some degrees of freedom and so on, but you can do it. And I claim it is controlled. So I stand by that. That field theory as being like the field theory for that transition. Yeah. Okay, so so now for the rest of the talk, and that's the new stuff, I want to convince you that, well, some of that physics can emerge entirely in classical systems and can be understood pretty easily from the framework of fluctuating hydrodynamics. Okay? At least in the case where you have this conserved quantity. I'm not going to talk about the outer phase transition without symmetry. And in fact, you can define such phase transitions as well in the context of just classical systems as some kind of classical inference problem, where you have some partial data and you try to reconstruct something, in this case, the charge of the system. Okay, so for the rest of the talk, I'm going to be forgetting about quantum mechanics. And I'm going to imagine I have a classical system, and here this classical system, this could be pretty much anything you want, but so for this talk, it's going to be, let's say, a Markov process that also has a conserved quantity. Okay, so it's some symmetric exclusion process if you want, something like that. Or it could be a stochastic PDE, say fluctuating, like a noisy diffusion equation. Yeah. And you notice that you can kind of define exactly the same problem of what I gave you for this type of system. So you can initialize your system in, systems that have a different charge, and then run it through this evolution and define measurements. Okay, so I have to define what a measurement is, but let's say you could imagine that you have some partial information about, you take one solution of your PDE for a given noise realization, and you, I don't know, measure charge at some space-time location, and you define this as your measurement outcomes. Okay. And you can ask exactly the same question of whether you can guess the charge of the state from that information.
Yes. The quantum system before was deterministic, right?
Yeah, but there's some randomness from quantum mechanics in the measurements. Right. So because it's quantum, when you measure, there's definitely randomness there. Yeah. So it could be, it depends, I should say, right? It could be a random quantum circuit, in which case the time evolution is random in time, but that is not important to the physics. The gates could all be the same. There's some intrinsic randomness from the measurement outcomes.
Do you need the randomness there?
Well, yeah, okay, so here there'll be noise, and the noise is important. That will be my randomness here. Yeah.
So in the case of quantum mechanics, you have unitary evolution and measurement, right?
Yeah.
Do you also have some such a distinction between two?
Well, no. So here I won't have unitary evolution, but I will define what the measurements are. Yeah. So that's maybe what this slide will do. So I'm going to define condition ensembles of my classical dynamics, even some measurement outcomes. So let me try to formalize this, and maybe we can see if that makes sense. So okay, I'm doing things in a continuum. So for example, I'm going to define something like a weak measurement. So if I have a solution rho of like this dynamics, I'm going to define some measurement outcomes. Instead of calling them M, I'm going to call them rho 0 here, by say being distributed according to that Gaussian. Okay, so that's the analog of what would be a weak measurement in quantum mechanics. So I'm measuring everywhere, but in a weak way, and gamma is the strength of that measurement. Okay, so if gamma is large, then rho 0 will be pinned down to rho. Okay. So this is, okay, so that defines my measurement process. Okay, so that's what I'm going to call the measurement, and it's weak in that way.
So weak means it's like imprecise, like.
Yeah. Yeah, so you could do it, again, like I'm going to also do it on a lattice. If I had a lattice system, I could also do strong measurements and sprinkle them random. This allows me, this will be much better for field theory, but the conclusions will not depend on that. Yeah. And so once you have like this guy, you can define a joint probability to observe both rho and rho 0 from the probability to see rho from that equation. And if you marginalize over rho, you will define the probability to observe a given measurement outcome. So that's the analog of a Born probability. So this guy is the probability to observe a given rho 0 from my dynamics. Okay. And if you do some very simple Bayesian calculus, you can also write down what a conditional probability of observing rho given some measurement outcomes is. So again, this is going from here to there is just Bayes' theorem, where, again, so this guy is what I'm going to call a condition ensemble, where I fix some measurement outcome rho 0, and I ask of like the condition probability to see rhos based on this measurement outcome. Okay.
Where do you get the Gaussian?
So the Gaussian is just me. I'm defining my measurement to be this. You'll see this will be like in disordered systems. You could make this non-Gaussian and it won't matter. It will be RG relevant if you want. Yeah. Okay, and so then I can define some averages at fixed rho 0. So this is again what I'm going to call the condition ensemble, where I define trajectories, like averages of that process, conditioned on observing a given rho 0. Okay. And I claim like this will be the analog of the quantum trajectories in quantum mechanics. So this type of condition dynamics of your process will be the exact analog, and this will be exactly like a Born probability. And you'll see that, again, if you prefer, so I wrote this in the language of field theory, but if you like lattice systems, you can imagine, again, you have a stochastic process, like a symmetric exclusion process. And then you condition it on like some space-time locations of having a particle here, not having a particle there, and do this in many locations. And then you ask of the condition ensemble of this Markov process and having those outcomes. This is what this is. Yeah. Okay, so then if you look at an observable average in that condition ensemble, and then you average over the measurement outcomes, well, you quickly realize this does nothing. Okay, so if you condition on something and then you average over whatever you conditioned on, then you're back to just averaging. This is the exact analog of like throwing away the measurement outcomes in quantum mechanics, of writing a quantum channel. So in order to see non-trivial physics, you need nonlinear observables. So if I put a square here, then all of a sudden this becomes non-trivial. Okay. Yeah?
The action S is you're going to introduce it.
Yeah, well, I mean, the action S is just the probability to see rho. So that will depend on whatever the process is. So here you could imagine you do MSR and whatever, and you write down what your action S is for fluctuating diffusion, which I'm going to do in yeah.
I'm still wondering about the difference between quantum case and classical case.
Yeah.
For classical stochastic models, as you said, you want to put some conditioning on the existence of particles at certain position, x and t. This kind of situation can be just considered by studying usual correlation functions, no? In the classical case.
Well, but again, you have to condition them, and you have to be careful when you average over the measurement outcomes to consider nonlinear observables to get something non-trivial. And that is actually the same in quantum mechanics. If you consider things that are linear in your density matrix, and you average over measurement outcomes, you will just get a property of the quantum channel, meaning it will not see those transitions. So you need things that are nonlinear in the density matrix. So this is really as close, like basically it's basically Bayes' theorem is the same as like Bohr's rule in some way, in that way here.
So for stochastic field theory, you can some kind of noise depending on x and t. For me, this looks like something related to what you
Sorry.
If we kind of formulate something like set as a stochastic field theory,
Yes.
we can introduce source term, right?
Yeah. I'm going to do that. So that's my next slide. Yeah.
You are saying that something similar can be done also for quantum measurement case.
Well, not in general, but I'm talking, okay, so this is specific of having a course of quantity, right? I'm also like, okay, I'm claiming like this learning process of charge can be traced entirely for classical systems. Yes. And that field theory that I wrote and that we derive in the quantum context shows up as well if you define that problem in the classical system. And it has the same interpretation in terms of learning the charge.
So here you are considering the classical stochastic system so that you may have the description using the Fokker-Planck equations.
Mm-hmm.
And the Fokker-Planck equation have the kind of the probability distribution function for the charge density. And could you, so is this P a conditional ensemble? I mean, could you repeat, explain the difference with the calculation in the Fokker-Planck formalism and this condition ensemble?
So, I mean, I'm not phrasing it in terms of like Fokker-Planck here, but hopefully it's. I'm just saying, like, you know, again, if you have a system stochastic, right, I can define what P of rho is. I'm defining what rho zero here is, the measurements is from this, right? So I can write down a joint distribution for rho and rho zero. And from that, I can marginalize over rho, that defines this guy. And from Bayes' theorem, I can just write this. That's right, and that's the condition probability to see rho. Condition on seeing rho zero, right?
Planck is already the average.
Yes, that's already the average also, yeah. You don't want to average too quickly. Thank you. Yes.
The observable for charge sharpness in this case is just going to be the variance of this conditional distribution?
So I'll get to this.
Okay,
yeah, so I should actually try to get to it, yeah. Okay, so let me actually try to go further, but okay, it's important that we have the setup. Okay, the setup is the most important thing because the rest is actually fairly simple. So hopefully then the next steps are sort of clear. Well, you could do this for a specific model, so let's do it for just a diffusion equation, okay? So everyone's favorite model in this room. So I'm just gonna take a noisy diffusion equation and do the usual MSR stuff, okay? So there's one technical thing that, okay, the one thing that I'm not explaining is you need a replica trick. And the reason is, okay, if you go back here, I said like if you average here, it's trivial, and if you put a square, it's non-trivial. It's non-trivial because there's a z of rho zero in the denominator, and then averaging is hard. And in order to average the things in the denominator, we need to introduce replicas and take a replica limit. Okay. If you want details on this, we can chat afterwards. But okay, so basically you need to take copies of your system, and then you can average over your measurement outcomes. But otherwise, okay, so everything else is relatively straightforward. We can play the usual games. Okay, I start from this, that's what I call z of rho zero, right? So I put usual MSR first step, but I put this exponential that corresponds to my measurements. And you introduce a conjugate field, you integrate out the noise, and at the last step, you integrate out also the measurement outcomes. And I wrote down the resulting field theory that you get. So the first line should be familiar. Okay, that's just the usual MSR action for diffusive particle, but I've replicated it, so A's are like the replicas, I have copies. And the role of the measurement is the second term. Okay. So the second term is like an interaction between your replicas that comes from like those measurements. Okay. And again, it's really just a few lines of algebra to get this. So if you want the details, you can ask me, but okay. So I claim like this provides a field theory of this monitored problem, okay, where the measurements are encoded in some effective interaction between your replicas. So you want to solve this theory and take this. So Q is the number of replicas, and you want to take it to 1 at the end of the calculation. So the good news is this is so here I'm measuring charge density. Okay. The good news is this is a Gaussian action. So that's, you know, a theory that even I can solve. So well, good. So you can diagonalize the replica structure of this problem. So you can define something like a center of mass, like wow, that's like average over replicas, and you can define like relative coordinates. So the intuition is like this center of mass is something that will not see the measurements. This will be the analog of the channel in the quantum case, whereas like the measurements will couple that guy. Okay, so then you can trust me, like this is a simple quadratic action, so you can solve it. So you can, for example, if you wrote down like just an effective action just for the conjugate field phi, it just looks like a free boson. Okay. Or if you want, again, you can write down just the full propagator of that thing, and I did that for you here. Okay. So what you're supposed to see is, okay, without the measurement, that's the usual diffusive propagator. But the measurements are relevant. They dominate over that term. Okay. And you see that at low energy, you'll just get a dynamical exponent 1 out of this. Yes?
Is the difference that in the usual EFT, I would not be able to write a row square term, but here you can write a row square term?
Yes. So effectively, you have a row square term, right? Yeah. Yeah. So that term is not something you would normally write. Like, yeah. But here it comes out from my measurements. Yeah. Yeah. Yes.
Sorry, this sigma gradient phi, what guarantees that this phi is gapless?
Well, okay, so just invert the matrix here. Yeah. Just,
but from the, I mean, I think the second term that is the diffusion, and the first term the sigma square. Where's this coming from? Maybe I just missed it.
So where's coming the k square here?
No, in the previous slide.
Yeah.
This term in the Lagrangian with sigma square.
Yeah, so that's from the noise. Yeah. Yeah, so that's from the noise, and it's conservative noise, right? So that's where you have the k squared, right? Yeah. Yeah. So the k squared is because it's diffusion, it's conservative noise. Okay. All right. So and I think that this gives you a field theory of what the charge fuzzy phase is, and it has dynamical exponent 1. And that's like this time scale of order L I was talking about. Okay, so T was going as L, has dynamical exponent 1, and that's what you recover from that field theory. So you can actually, write down, like you can test predictions of that field theory. So this is going back to things we did in the quantum case. But that field theory, okay, so I haven't talked about the transition yet, and I hurry up a little bit. But that field theory in 1D will tell you that equal charge correlations go out of 1 over x squared. Okay, this is what this propagator tells you if you just go back to real space. And so you can check this in a symmetric exclusion process. Okay, so you can take lattice realization and you do measurements, and here we actually do strong measurements, meaning like we pin down again what your particles are not. And you could look at a charge correlator, and we see that it goes as 1 over x squared. It also means that the charge variance goes as
P corresponds to gamma in the...
Yes, so P is, sorry, I'm switching notation a little bit, but yeah, my field theory. So this is something you can check in a lattice model. So you see that you immediately go from diffusive scaling to something that looks like it has relativistic invariance, okay, from the measurements, which is somewhat interesting. So let me say that, okay, so you get a new, call it monitored z equals 1 fixed point that we call charge fuzzy. And it really results from the measurements and the noise term in your fluctuating hydro description, like this k squared. So you can immediately generalize this to whatever, fractal hydro, think of Levy flights or other things. You can take different types of hydrodynamics if you want, and write down, other type of fixed points you might get from this. You can also monitor something else. So here I was monitoring charge density. You can monitor currents. You can ask, what if you can only measure a gradient, for example? If you measure gradient here, this becomes marginal, and so that changes time scales, for example. So you can really play it, many games of like different things you can measure